ECE Distinguished Lecturer Program. So today we have the pleasure of having Professor Setti from Bologna to come and talk to us. And Enrique, you going to do the introduction?
Sure, yeah. Okay.
Excellent.
So thanks everybody for coming. It's a pleasure to introduce Gianluca Setti. He's a faculty in the University of Ferrara. So a fun fact, I think this university was founded in 1391, so 100 years before Columbus came to America. There's a lot of history there. But also most interesting that he did his PhD in Bologna, which is actually the oldest university. So anyways, it's a pleasure to have him here. He's won several awards, including the Darlington Award, which I particularly like because it's an intersection between theory and applications. And he has published more than 260 papers, as I said, several papers awards, and a role model also for service, like being editor-in-chief in the 2 transactions of Circuits and Systems, part 1 and 2, and also president of that society and vice president for publication services, and the whole name is and products. So with that, I would like to, he's going to talk, by the way, about intersection of theory, like compressed sensing and dynamical systems, and their application to circuits. So thank you for being here. It's going to be a lot of fun. Thanks.
Thank you. Thank you. Thank you for the introduction. It's actually a great pleasure being here today and talk to you a little bit of this idea of trying to exploit. The idea really is try to exploit statistics in a constructive way to try to optimize the performance of your circuit, of your system. So just before starting, I would like to acknowledge the fact that what I'm going to present here today is not absolutely the result only of my work, but a lot of great people I had the pleasure to work to, some of co-workers and some former students which are now faculty themselves or working in industry. So what we are going to talk today is exactly the idea of having the basically your engineering system whose performance you can actually express as a function of a suitable algorithm. And on the other hand, you have your algorithm, which depends most of the time on statistical features. And as engineers, we are all trained about Gaussian IID. We love Gaussian IID because it's easy to treat, it's easy to obtain expression in closed form. But most of the time, we give it for granted. So, and it may well be that if we just play with the statistic of the signal there, we may end up in trying to optimize performance of the system we are dealing with. So basically what I'm going to present today are 2 examples of that. The first one is dealing with the acquisition of signal using a slightly improved version of compressed sensing that we developed. And the application is going both the implementation of an analog to information converter and taking advantage of that, and also trying to, for instance, have other application like considering a system for the acquisition of EEG signals from evoked potential. The second example, which will be treated in less details due to time constraint, is going to be the use of a chaotic map as generator of a signal with statistical features, and use that to improve electromagnetic interference reduction using a split spectrum clocking methodologies. And I will have no time to give you details on how you can actually efficiently implement a random number generator which are CMOS embeddable. Okay, let's go with the formal outline with the first part. I will try to give you a 4-slide introduction on compressed sensing, and most of you are familiar already with that, but just to to establish some common language. And then we will deal with analog to information conversion and try to see how we can actually improve the straightforward architecture that one can consider, which is the random modulation pre-integration. And we will see that in order to do that, one of the points we are going to make is to improve the compressed sensing acquisition using a property that we called rakeness, which is actually nothing but a suitable design of the sequence statistics in order to be tuned somehow to the family of signal that you want to acquire. We will deal with the RMPI architecture implementation in 0.18 micron CMOS technology, a project that we did with Texas Instrument. There is a huge to tell here in terms of a smart way to deal with some unidality of the circuit, or a way out to test this analog to information converter, because this is completely uncharted territory. This is not an analog to digital converter, but I have no time for that. I will simply present some measurement performance and deal with some applications in which, again, this rakeness idea give you some advantage in terms of signal acquisition for electromyography, and EEG signal acquisition for recognizing schizophrenic patient. And again, in this case, CS will be used to filter directly the signal after acquisition, so you can actually save some filtering stage that are classically present due to that. Okay, so let's start with this 4-slide introduction on compressed sensing. So what is sampling? You know, it is a projection, as we all know. And depending on the particular value of the function phi, we can have actually the classical Shannon sampling, so in which these functions are actually delta-like term. And therefore, actually this value y are actually not but the sample at with a period with the sampling period which is capital T. And we all know that this is the most general approach, then can be applied to any band limited signal, and it has a balanced need of resources between acquisition and reconstruction. So acquisition is easy, and reconstruction is also very easy because it just needs a low pass filter. What compressed sensing want to do is simply want to replace the waveform here with a pulse amplitude modulated signal, whose amplitude are actually IID random variables, theoretically Gaussians. And so instead of having a delta function here, I have this function here, or the function there, and so on. And what I want is to acquire sample YE, which I can express as a weighted sum of the sample of the original signal. And the claim is that I can acquire the signal and be able to reconstruct it using much less sample than with the for the Nyquist rate. So if Nyquist require n samples, I want to do that with just m samples. So the issue is, does it work, and under which condition this works? Well, in order to show this, let's assume that my signal is actually a vector. It could be actually the vector containing the Nyquist samples of the original signals. And I can express it with respect to a suitable basis, which is defined by the function, by the vector psi. The signal is called sparse, can be expressed using only a very few element of this basis phi j. So the function can be expressed in this form, where the matrix psi collect all these vector of the basis, and where this vector alpha has only k, with k much less than n element which are non-vanishing. So if this is the case, then this is the classical picture that everybody has done compressed sensing have seen. So what I want to acquire is only this m sample here, starting from the signal x, which can be expressed in this form since the signal is k sparse. So there are only few elements which are non-zero in this vector here. Then I have this matrix phi, which collects all the vector of random variables which I have seen in the previous slide. And this matrix here has m row and n column. And therefore, what I'm doing is a dimensionality reduction, because I'm passing from a vector which has n dimension to a vector which has only m dimension. And that's the key in compressed sensing. So when this is working, of course, if the signal is sparse. So I must acquire sparse signal. So I must have I must have some prior knowledge of the signal that I need to acquire. And also the second condition is that the acquisition matrix phi must be, and with respect to the sparsity basis psi, they must be incoherent. This means that their coherence, so the maximum product, the maximum scalar product between any two vectors of these two matrices, must be as low as possible. intuitively speaking, this means that the element of the vector of the matrix psi that I'm using for acquisition must be properly aligned with respect to the element of the basis of sparsity psi, so that when I'm going to project the vector, the unitary vector of the sparsity basis into the space defined by my acquisition matrix, these projections are maximally distant. So they can be distinguished as much as possible. So let me give you an example in a three-dimensional space here. So what I have are the sparse signal. These are the red signal, which goes, they have one component over 3, and therefore they are sparse in this three-dimensional space. And since they are sparse, I don't need it to sample it using 3 samples. I just need less samples, and these less samples are obtained by considering the projection over this plane. So what I want is that if I take this vector here, whose projection is that one, or I take this vector here, whose projection is this one, or the vector here, which has one element on the third axis, whose projection is this one, what I want is these three projections here, here, and here, here, and here are maximally distant, so their angle is 120 degrees. And that's basically, the incoherence is simply a generalization of this concept. The other concept that I need is the fact that the matrix theta, so the product between phi and psi, is almost an isometry. This can be formally defined by saying that it satisfies the so-called restricted isometry property, which is reported here, which simply means that when I'm going to make this projection, I'm losing as less energy as possible. And the reason is that since noise will be there, and since any projection basically don't do anything to noise, so noise will be always there and will have all the same intensity no matter the projection. I cannot lose too much energy due to this projection if I want to recover the signal with a larger enough signal-to-noise ratio. Okay, so why we said that we must have Gaussian random variable? Because one can actually easily show that if these elements in the acquisition matrix are Gaussian random variables, then incoherence is satisfied no matter the signal I want to acquire. And if I use, again, this hypothesis for Gaussianity for random variables, then the matrix theta satisfies the restricted isometry property. So everything works nicely and very well. In terms of decoding and reconstruction, in order to make the reconstruction, I need to solve, well, there is a whole theory behind, but practically speaking, I need to solve this minimization problem. So I take the vector, which is the sparsest one with respect to an L1 norm, subject to the fact that it must give rise to the measurement that I can actually, that I have obtained, and this is the so-called basis pursuit problem. Obviously, this in the ideal case in which there is no noise. If there is noise, I need to satisfy this constraint, while this quantity epsilon square is linked to the level of noise that there is in the system. What Candace and Dono have proven is that if the value of element that I'm going to sample using this new value for acquisition of the system, this compressed sensed acquisition, is large enough with respect to the level of sparsity, with respect to the dimension of the original vector, and with this coefficient which depend to the matrix theta, then I can give good reconstruction with probability 1. In practice, M is the order of 4 times the level of sparsity in the system. There are plenty of algorithms which are going to be used to solve this minimization problem, and actually finding the best one is still an open problem. So everybody is using one depending on their particular task at hand. Every algorithm has different properties, and this is still an open question. But if you want to just look at compressed sensing from an high-level perspective, basically what it is compared to the classical Nyquist sampling is not a fully general approach, because it requires the prior of sparsity, and also it is not balanced in terms of resource used, because it uses low resources in terms of acquisition, so I acquire less samples in this case, so I can do it using hopefully less energy. And it needs definitely more resource in terms of the reconstruction, because you need to solve an optimization problem. The good news is that most of the signal, in particular the biosignal, are actually sparse. Therefore, compressed sensing works for these signals. And it is an excellent way to reduce the energy which is necessary for the signal acquisition, or it is thought to be an excellent way. And the natural application for this technology are in body area networks and obviously also for the Internet of Things nodes. Just to give you an example of the fact that this works, so this is an example of a ECG signal which has been acquired. Okay, there is 1 second of signal which has been acquired with a frequency of 250 Hz. So 256 samples are those necessary for the Nyquist acquisition. In this case, I've used 55 measurement using compressed sensing. So I have a compression rate which is 4.7, so the ratio between 246 and 55. So as basis, as sparsity basis, that's not really a basis, a dictionary, so it is overcomplete, but that's a detail. These are Gabor times frequency atoms, and in terms of the matrix, it is a Gaussian IID random matrix. So when you go to the intrinsic signal to noise ratio was 17 dB, because these were actually not real ECG but were synthetic ECG in order to inject the level of noise that we wanted. The figure of merit in terms of reconstruction was the average reconstructed signal to noise ratio, which is the ratio between the original signal and the error committed in reconstruction. And what you get here is the original signal in red and the reconstructed signal in blue with an average reconstructed signal to noise ratio of around 15 dB. So they resemble reasonably well the original signals, at least in the terms of the mean features. And if you want the representation of the average reconstructed signal to noise ratio as a function of the compression rate, you can see that obviously as the more you compress, the less quality you get. Therefore, if you want to improve this, you can actually reduce the compression rate. And in fact, if you reduce it to here it is to a value which is 3.5 here, you can get a much better reconstruction of the ECG signal, which is actually in this case a real one.
Question?
Yes.
So I mean, I guess I'm used to calling it the SNDR. Why do you call it the average?
Because it's actually is done not only with respect to a single, but it is with respect to a lot of instances. Yeah, it's an ensemble. So the 15 value I give you is with respect to the ensemble. What I'm showing is obviously one instance. If you want to go to, if you want to go a hardware which is actually taking advantage of this particular frame, basically what you need to do is to implement a system. The most straightforward way is to implement a system which actually does this operation, which is simply an architecture which is called the random modulation pre-integration. That's not the only architecture which does compressive sensing, but it is the one which is the most general, so the one which can process any kind of sparse signal, while the other one have all kind of restrictions. So if you want to acquire M sample, one way to do it is actually replicate this structure M times. So you need actually for doing that M times an analog to digital converter, which is going to operate to a frequency which is n times less the Nyquist frequency. So you gain in advantage in terms of the energy that you that you use for every operation of this converter, but obviously you have all the energy which is necessary to power up all this part of the circuits. But there are other issues here. The first issue is that the guy here is theoretically an analog signal, and therefore you may have issues in terms of precision of the signal that once you are going to implement it. And if this is an analog guy and this is an analog guy, this multiplier here is an analog multiplier, which is a big no for anybody doing analog circuit design. Then you have the fact that an operational amplifier that is here may actually saturate, and this is actually going to completely change the dynamic of the system, and also the fact that you may have actually M converter which are needed. So let's see if we can basically change the structure of the system in such a way that we are trying to improve all these points. So the first the first problem is actually quite easily solved, because if you replace Gaussian IID random sequence with binary, antipodal, IAD random sequence, everything works pretty fine. So this was proven a few years later. So this is instead of a plot of a paper of ours, since this was published before the proof was actually made. So actually what is reported here is, again, the average reconstruction signal-to-noise ratio for the same signals, different level of sparsity for the blue, purple, and yellow plot. And you can see that the acquisition using Gaussian or binary as perfectly superimposed, the performance are absolutely the same. But why it is interesting? Because multiplying by plus and minus 1 and doing an analog implementation in discrete time, which is a switch capacitor 1, means simply to inverse polarity, and therefore basically using a couple of switches. You get rid immediately of the analog multiplier. So nicely done. For improving, again, the structure of the system you need to implement, actually you may consider an approach from the algorithmic side of the entire structure, and considering the fact that standard compressed sensing is using IAD Gaussian random sequences to be as general as possible. In theory, it can acquire even white noise with doing that. But it's actually true that the signal that you have to acquire will not only be sparse, but their energy will be confined not in the entire frequency domain, not in the entire space, but in a sub-region of that, for sure. For instance, this is the power density spectrum of a typical ECG signal, so which is a low-pass signal. And therefore, since you know that the energy is concentrated in the low part of the spectrum, why not to take advantage of that by trying to design the sequence so that they are actually trying to maximize the energy which is acquired exactly in that part of the spectrum. And this is the idea which is behind a concept which we call rakeness. Rakeness because it reminds the effect of the rake receiver, so it's trying to extract as much energy as possible from the sample. So the terms, obviously, it doesn't exist in English, and by the way, the translation doesn't exist in Italian too, so we just made this thing up. But the idea is simply that you want to design the acquisition sequence phi in such a way that you are actually going to maximize the expected energy which you are going to extract by projecting the signal X over the acquisition sequence. So you really want the sequence which are the solution of this problem, subject to a constraint which tells you that, of course, the sequence must have a finite energy, and also that the cross correlation of this sequence is low enough to maintain the fact that this sequence must be random. Otherwise, you would acquire all the time the spherical component with as maximum energy, and therefore this would not be at all working as compressed sensing should. Okay, so how can you do that? Well, if this would real value, what you need to generate is actually what this guy give you is the cross correlation, or if you want, the covariant matrix of the process, and you need to generate a process which is characterized by a given covariant matrix, or if you want, by a given spectrum. If this was made by a real value number, that was the easiest problem possible, because you could design a filter, excited white noise, done. But the problem is that you want plus and minus 1, and that is much less easy to do. Actually, it's a kind of hard problem. The problem is also that you want a matrix which is the matrix that you have and the solution that you must have must also be a correlation matrix, and therefore must be positively defined. And what we came up with is a system which is the one described here. This slide is actually a paper in itself, so I don't comment too much on that, but I can give you a lot of details if you want to. So if you take this system, which is formed by a comparator, you have one of the input of the comparator is a random number, and in the feedback loop you have a finite impulse response filter, was transfer function is linked to the spectrum of this plus and minus 1 sequence that you want by this equation. So the solution of the previous problem give you the autocorrelation function. Therefore, again, in equivalent form, the spectrum of the signal. Once you have the spectrum, you can invert this equation here, and this is the trick because this must be inverted in numerical form to obtain the function f. Once you plug the function f here, this machinery gives you the sequence that you want. So you have this machinery, this one solved, and this is exactly the machinery which give you the chunk of the plus and minus 1 sequence that you want to plug into the matrix. Just to tell you that this works, the green line is the spectrum that I wanted to generate with this machinery, and the black one is the simulated spectrum of the plus and minus 1 that I obtained from the machinery. So this is what really works pretty fine. Let's apply this to our ECG signal that we've seen before. So this is the spectrum of the signal that you want to acquire. As you can see, IED sequence were obviously very flat, and the spectrum of the acquisition sequence that are the solution of the problem mimic the red one, even if they are not identical. And this is the result you get. So this is the acquisition and reconstruction segment of an ECG signals using standard IID sequences. And this is what you can get if you use the improved sequence. So the quality is certainly better. And if you want to see this in terms of average reconstruction signal to noise ratio as the function of, again, the compression rate, you can get that what you can get with this localized sequence, this Reyknes-based sequence, is basically all the time 4 to 5 dB higher than what you can get with standard IID sequence. And this is basically the result on this paper that we published in 2012, if you want to additional reference to that. So if you go back to the structure that we want to implement in terms of yes?
So using the rate sequence, you improve the SNR?
Say it again, sorry?
So your intrinsic SNR was
yes.
10 dB, and then after you think you...
Okay, I had this question only twice in all the time that I presented that. Well seen, that's absolutely the case. And the reason is that the sequence are actually filtering out part of the noise itself. That's I have an example at the end in which this is done actually in an example of the EEG. So you are tuned so well to the signal that you want to acquire that you are doing intrinsically a kind of filtering effect as well.
Okay. So the ARSNR is basically the denominator
is
the difference between the reconstruction
yes.
with the noise-less
yes
signal, not
correct
signal.
correct.
Okay.
But that's a very good point. I'm happy. I mean, it means that people are not sleeping, actually. That's cool. So this is actually the structure of the AEC, the circuit level that we actually implemented. So this is this is a single-ended schematic, but actually the real schematic is fully differential. So there are 16 of these branches which correspond to the possibility to acquire a signal using m samples per step. With respect to, well, of course, this is simply a standard analog to digital converter, an SAR converter. With respect to what we've seen before, instead of having m converter, I have only one, which means that basically I am multiplexing here, and therefore the price I have to pay is that the frequency of acquisition here is not n time less the Nyquist frequency, but is m time larger. So I'm paying in terms of frequency here, but what obviously I'm saving hardware. So this is the structure. So I'm just jumping over all this part for the part of how to deal with saturation, which is again an interesting point, but in the interest of time, I'm jumping over that. And I'm showing you the picture of the chip which was implemented because I want to arrive to the measurement result. This is actually in processing with the chip of the signal which were taken from a database. So signal are not a real signal from a patient, but they are downloaded from a database and uploaded into the chip. So what I have here is the comparison between the original input signal and what I get with the standard compressed sensing acquisition. So in case I'm using, again, binary IID sequence, as you can see, the quality is quite low, and the reason is here is because with respect to this particular problem, in which basically I have 0.5 seconds, so 128 sample necessary for acquisition for Nyquist. So given the level of sparsity, the theory should say that I need 32 sample. I have only 16. I try to reconstruct it, and I get something which is, of course, not that great. But if I'm using the improved version, I get something which is actually quite nicely compared to what I had at the beginning. And also notice that I have 3 times here, and the reason is that I actually multiply the input, the signal input, so to provoke as many as possible saturation into the amplifier. But since I had a way to take this into account in my chip, basically the reconstruction is good all the time. While if I had not the case, this wasn't the case. Question.
So if you had used some kind of a dictionary learning approach, where you learned the example of what a fiducial of the ECG signal would be like, you probably would do a lot better with the standard. I don't know. This is certainly possible. So it means in terms of using a dictionary learning for the sequence, right? Right. So you basically have chunks of the signal itself as part of the. How it is possible to? I mean, how does this generalize? In the sense that this generalizes pretty well, and that's exactly the next slide. So if you take chunk of signal which are ECG of a sick patient, which has nothing to do with the ECG of the other patient, these actually reconstruct pretty well. The problem is exactly training with respect to overtraining, I would say, but this is something that is worth exploring and worth comparing. So it might well be that it depends on the cases. This one is kind of interesting in the sense that is done for an entire family of signals, and is actually, I mean, it generalized quite well with respect to that particular family. But this is something that is definitely is worth exploring. So just so I understand, so yes. Basically you're sampling the waveform unknown with your Rigorous approach, and then you're reconstructing based on the bases. Actually, the basis in this case is a Gabor basis. Yeah, but actually the reconstruction is the training of the sequence actually depends on that. Yeah, but what you need to have is really the localization of the energy and the shape, the correlation profile. What you need is the correlation matrix. Actually, the only thing you need is the correlation matrix of the signal that you need to acquire, the family of signal that you need to acquire. That's the only information that you need, which is kind of which is quite general. So yeah. I want to comment that there are degrees, right? The standard CS assumes nothing about the signal. That's correct. The dictionary approach assumes and this is somehow in between. And this is in between. I correct. That's exactly the point. And actually, there is no surprise that you are doing better because you are adding another prior to the system. So therefore, the more information you have, the more actually you can exploit. So that's exactly the same idea with electromyographic signals. So exactly same thing. And as you can see, you have 24. Measurement that we do, so we actually get to chip together in this case, and 64 were actually needed, and therefore again bad reconstruction, but good reconstruction if you use this improved version approach. And again, if you just go to a sick patient, in both cases you get good reconstruction even if these chunks were not typical electromyographic signals. Yes?
It is, but it has some specific features that, in any case, you seems to being able enough to capture. So the point is that you are really tuning the sequence with respect to the family to get the main energy there, but you still have enough generalization capability to be general enough in order to acquire any kind of signal anyhow. So you remain random enough in order to acquire all the signals. So it's really a trade-off, but it seems to work well so far. Honestly, again, in theoretical terms, we have a grasp why this signal is going there, so we have a kind of geometrical understanding why it's going there, but it's still something that is not proven. So we have an analytic solution of the Reckness problem, but why this works in the geometric space, so having the nice geometrical equivalent of what compressed sensing does is almost there, but there is something that we still don't grasp. There is that's a project that we did with in collaboration with some guy in Turin at IIT, and it's end movement recognition system. So the idea is to acquire obviously the potential, the EMG signals from the muscles. Actually, the set of sensor is simply there are really 16 piece of metals, nothing more than that. So it's really very rough. But if you want to acquire and transmit the signal, actually you sample them at 4 kHz using 12 bit per sample, 16 sensors. This means transmitting 6.5 megabyte per sensor, which is a lot of information. So you need to compress them, and we were trying compressed sensing in this case. Again, just a plot to show you that the Reckness-based CS is doing better than the standard CS, both in terms of average signal-to-noise ratio. That's a screenshot to show you that this visually is the case. But this is probably another interesting plot, because one represents the average recognition rate with respect to 3 movements that were the open end, a fist, and something in the position of closing, of grasping something. What is interesting here is that the recognition in case of non-compression is here. This is my enemy, so the best that I can do with this particular system, change the system, maybe I can have a better recognition. But what is interesting is that if I'm using compressed sensing, if I'm going to something which is almost a compression rate of 5, nothing changed. So I can basically compress, I can have a compression factor of 5 and basically transmit something which is going to be recognized in the same way. That's a project that we started since a student visited Professor Upshire at the University of Maryland, and this the possibility of doing some cheap acquisition of EEG signals for the idea would basically understand when a schizophrenic patient is actually schizophrenic. But one is far from there, but the good news is that the Reckness-based CS is actually quite good in acquiring the signals. And just let me show you 2 screenshots. This is basically what one is doing for filtering these signals is usually doing a 3-step approach. One is using a time shift PCA. The second one is using a sensor noise suppression for eliminating environmental noise, like the 60 Hz. And the other one is doing denoising source separation for taking consideration of sensors mismatch. And if you take into account what you have as, okay, the blue one is the raw signal acquired from the sensor which is at the center of the scalp. The red one is the filtered raw signal using the one to remove the problem due to sensors mismatch. And the black one is instead what you can obtain directly by acquiring using this Reckness-based approach, which was trained using the complete filtered version of some of the sample that you had. So you just trained your algorithm knowing which is the, say, real truth that you want to acquire. This is the spectrum of the signal that you get. The interesting part is that the 60 Hz is actually removed from the spectrum of the signal automatically if you use the compressed senses version, while you need an additional filtering effect an additional filtering stage if you use the standard design methodology. So basically you have a 3-step filtering. So we applied only one, so the one which did not remove the 60 Hz, and in fact the 60 Hz is still there. But if you use the Reyknes-based approach, automatically it is as if the 60 Hz filter was already present. And actually, and this is a paper that we have at ECE, and we have another paper which actually shows that using this Reyknes sequence, you can actually implement a notch filter just by acquiring the signal which, by using this sequence which are being developed in the right way. So this is another, again, scalp map to show that, yes?
So if 60 Hertz is repetitive and is there, why would it leave it out? I mean, is that an error not to have it?
Because the 60 Hertz is the, if it is there, if it is there due to the fact that there is an environmental noise, and as it is in that specific case, this is due to the, is there due to the error in terms of acquisition. So it's not a component which is there, which is natural. So the 60 Hz was there due to, is the error due to the, it's the power system noise.
But I'm just wondering
if I mean, well, it depends what it really depends is what is your, what is the truth. So what is the real signal that you want to acquire in terms of aging?
So if the power spectrum of the real family of signals had enough energy at 60 Hertz, then this would not happen. That's
correctly the point. So, yes, Pam?
I might suggest that the 60 Hertz was uncorrelated. This was a time response. This was a set of stimulus response library that was based on a certain experimental, auditory condition.
So
if the 60 Hertz in the experimental recording is uncorrelated with respect to the experimental stimulus, this happens.
Otherwise, I mean, it's basically it's what you really need to determine is what is your ground truth, and if you tune the acquisition sequence to your ground truth, it's basically as if it's providing a filtering effect. It's in itself, which is exactly what is happening here. So what you have here is that this sensor moved, and therefore you have much energy there due to the artifact. So if you apply the filtering stage for remove this artifact in the standard algorithm, you get the blue one is obviously the one with all the spikes, so therefore you have the artifact. The red one is the one which the standard filtering effect, and the blue and the black one is the one using Reyknes. So as you can see in the spectrum, the original signal has a lot of higher energy in frequency. The red signal has a reduction due to the effect of the filtering effect. But again, since we train the signal, the sequence of acquisition with respect to the ground truth, this again has been eliminated. So it's basically, it tells you that you may eliminate some of the filtering stage. It is like as it was acting really as a rake receiver to some extent. So it was filtering out all the unwanted noise and really tuning to the information that it needed to acquire. Yeah. Well, the ground truth is really taken from the acquisition, from the signal which has been measured, and applying the standard three-step procedure for denoising it for some of them. So if this is state of the art, so this is my state of the art through, I train with that my sequence, and then I apply it to another set of signals which have been again recorded, not the same one obviously, and then I'm seeing exactly the result of that.
That's also the reason why you
yeah.
have the drop in 60 Hertz.
Yes, exactly the same. That's just because it was eliminated by the fact that it shouldn't be there. If you just determine that this is an intrinsic effect physiologically and you don't want to eliminate, you don't eliminate it, and you train, you basically solve the problem, and the sequence will not eliminate the 60 Hz. Okay, so just go to the conclusion of the first part. So it's, well, compressed sensing is a set of theoretical tools which has been found application in acquisition of sparse signal, and is a clear example, well, trying to tune the algorithm with respect to the circuit that you want to implement can actually move you a long way. In terms of, for instance, by changing the requirement for Gaussian versus binary sequence, one can reduce the complexity of the analog to information converter. Coping with saturation is also possible. I'm happy to give details on that. And also modifying statistic of the sequence acquisition algorithm give you a few advantages. Let me give you just 10 minutes more details on the second part, which is trying to reduce electromagnetic interference using nonlinear dynamics and using chaos. So let me try to start by telling you what chaos is. So I consider a very simple circuit, which is a tent map. So if you take the input-output relationship of this bunch of MOS transistor, you get exactly this function here. And if you take a sample and hold in the feedback loop, what you get is this evolution, which is aperiodic at steady state. So chaos, phenomenologically, is an aperiodic steady-state behavior that is not an equilibrium point, is not a periodic motion or a quasi-periodic motion. And also it has specific features in the frequency domain, because it has a broadband normalized spectrum, which is nothing similar to what you get with a periodic or a quasi-periodic motion. The most interesting features of chaos is, the most particular feature of chaos is the sensitive dependence on initial condition, which means that if you take the same system and you let it start from two slightly different initial conditions, you expect that the two trajectories are the same. Actually, they are not. After a few time steps, they tend to become uncorrelated, which means that the system is naturally amplifying any measurement error, any measurement in any error in the knowledge of the state, so that at some point you basically lose track of where the system is, even if the system is deterministic. So chaotic systems are therefore, chaotic signals are therefore broadband noise-like, generated by a simple circuit and unpredictable, and therefore chaotic circuit can be used as implementable CMOS embeddable noise generator, assuming that you need one. Can be used then to improve performance in a system? Well, actually, in order to try to answer this question, we need a much more practical characterization of chaos from an engineering point of view. And in order to do that, one actually can study the chaotic behavior from a statistical point of view. So the idea is you have your map, so a one-dimensional discrete time dynamical system whose update state equation is the one here. M is a function of the interval 0, 1 into itself. And instead of saying that I know the initial condition and I'm going to look at the trajectory, I assume that the initial condition is drawn according to a certain probability density function. And then since the state at time step 1 is the nonlinear function m applied to this random variable, I want to know which is the probability density function which describes the state of the map as a function of the probability density function according to which I draw the initial condition rho 0. And I can do that at step 2, step t, and so on. To see if this makes sense, one can actually make a few numerical experiments. Assume that you take two truncated Gaussian PDF, and you draw randomly 1,000 initial condition from each of these two distributions, and you represent them in the interval 0, 1, which is here, divided into 100 parts. This is the histogram representation of the first set. This is the histogram representation of the second set. These represent exactly the PDF according to which I draw this initial condition. I take the logistic map, so this nonlinear function here, for x multiplied by y minus x, and I apply this function to the entire set in green or in red, and I obtain this evolution here or this evolution there for the two sets. After a certain number of iterations, the distribution actually looks the same and more or less very close to this quantity rho bar, which can be proved to be the final density. This means that if I'm iterating the map large enough, the state distribute with respect to a distribution here, a density here, which I'm able to say it's always the same, or at least in this experiment looks always the same. If I change the map, things look pretty much the same. Simply what I'm changing is the final density. So actually, it seems that there is a final density all the time, and that it's depending on the particular shape of the map. Changing the map actually changes the density. And that's actually the case when I can actually define a mathematical operator, which is called the Perron-Frobenius operator, which is related to the map that I'm using, which let evolve the density, and if I'm applying it to the initial density a number large enough of time, I obtain this final density rho bar. So what this theory, which is called ergodic theory, does, instead of studying chaotic map from in a time domain, is studied it in an adjoint domain where I have a discrete time system again, where the state of the discrete time system is the probability intensity function of which describes the distribution of the real state, and where the evolution operator is a functional operator but is linear. So instead of using a highly nonlinear dynamical system, I'm studying in a linear dynamical system but in a functional operator space. It's interesting because in general it's actually quite difficult to compute rho bar, and to compute also another important point, which is how fast I have this convergence. Because I should actually compute the fixed point of the Perron-Frobenius operator to compute rho bar, and I need to compute this quantity R mix, which is called the rate of mixing, for computing the speed of convergence. These two quantities are very difficult to compute in general, but that's not the case if I'm using maps which are called Markov maps and which are linear in each of these regions, which are called piecewise affine Markov maps. The map is Markov because if I consider the interval 0, 1, I divided it into, say, 4 parts, not necessarily equal. These are equal. And the map is Markov. Each of these subinterval is going to map in a union of the very same subinterval. So x1 is mapped on x1, x2, x4. x2 is mapped in x1, x2, and so on. Well, if I'm taking these particular kind of maps, I can get a lot of information by constructing this matrix, which is called the Needing matrix. So if you look at the element at the intersection of the jth row and the kth column, you can see that this is simply the fraction of point in xj which are going to be mapped in xk after one iteration. In fact, this is the set of points that start from xj and goes on xk after one iteration. And if I want to take, for instance, the element which is at the intersection of the third row and the second column, I need to take the interval x2, take its counter images with respect to the interval x3, so which is this piece here, so which correspond to this interval here, and take the length of this interval with respect to the interval of the length of the whole interval x3, which is exactly 1/2. So if you take this expression here, and instead of looking to a measure here of an interval, you read here probability. What you have here is that this is the probability of the event. The state of the map starts from a point which is on xj and ends up after one iteration in interval xk. So it is a joint probability. At the numerator, you have the probability of starting from xj. So you have joint probability over probability. This is a conditioned probability. And in fact, these map represent the transitional probability of an associated Markov chain with respect to the Markov map, which has one state for each interval of the Markov partition. The good news is that this map is an approximation of the Perron-Frobenius operator in the space of simple function, actually. So which means that I can extract information from this matrix instead of using an infinite dimensional operator. And the good news is that if I take the left eigenvector of this matrix K in the space of simple functions, so the functions which are boxes in the interval x1, x2, x3, x4, I can get exactly the expression of the invariant density. So that's an easy way to compute invariant density, and is also an easy way to compute the rate of mixing. That's actually, there is a huge theory here, so I'm not giving you a lot of details on that, but one can actually, if you take quantization of this sequence, you can actually compute in closed form all the correlation function, any order moment of all the sequences which are generated here, which means that you take the map here and you actually can completely characterize these from a statistical point of view. Or if you want sequence generated from with some statistic, you can end up with a map which you can implement and actually gives you the sequence with the statistic that you want. So actually the news is that in order to give you this chaotic map are actually random process generator which tunable statistical feature which is easily implementable in CNOS technology. 2 minutes to give you why this is useful for EMI reduction. So this is a typical circuit which has problem with electromagnetic interference because it is actually driven by this periodic signal, and therefore all current and voltages are periodic and emit energy conducted or radiated at harmonics. So usually what people do to get rid of this electromagnetic interference is to put in a filter or getting a screen. These increase the cost of the entire apparatus, and there is actually no need or no a priori guarantee that you are going to solve the problem of electromagnetic interference. So what people came up with is an idea of trying to, instead of having a periodic signal here, having driven a signal which is slightly perturbed in such a way that instead of having high concentrated energy corresponding to the harmonic, you are going to actually enlarge the spectrum and reducing its peak, because that's exactly what you need to measure in terms of electromagnetic interference. The norms tells you that the peak value of the interference should be below a certain level. So you need to introduce a modulation, and how you do that? Usually there are different ways, but the frequency modulation is what it is the most interesting in the literature, and obviously the performance depends on the expression of on a particular modulating signal that you use. If you use a sinusoid, the spectrum in the Carson bandwidth, which is the frequency of the unmodulated signal minus the frequency deviation and plus the frequency deviation, look like that. It is U-shaped, and this is suboptimal because you have these two peaks which are larger than they could be. So, and these depend on the shape of the law. Once you have understood that, you can modify this modulating signal in this way. That's a QB profile, which was patented back almost 15, 20 years ago, and is used actually today in product from Texas Instruments, Fujitsu, Cypress, and so on. And in fact, the spectrum is pretty much flat. The problem still is that this is a periodic modulating signals, and therefore you are not spreading the energy in all the spectrum that you have at your disposal. You have, again, line in the spectrum. It would be much better to have a continuous spectrum. And the idea is, let's use a chaotic signal which is broadband. To see if it works, you need to compute the spectrum after the modulation. Well, it is lengthy, but it can be done. I'm not commenting on the structure of this formula. I'm simply telling you, look here. This formula is valid if R mix is low enough. You remember the value of R mix before, therefore it's important to compute it. And the statistical dependence is in the expectation, which is done with respect to the probability density function of the map. And it is a function also of the modulating index M, which is the ratio between the frequency deviation and the updating time of your map. What is interesting is that if M is large enough, the spectrum is actually proportional to the invariant density of the map. This gives you an easy way to do optimization. You want something flat. And in fact, if you take the W map we've seen before, remember you had that the rho bar was higher here and lower here. So if we go back, oops, and you want to see the spectrum, if I'm using this map inside this modulator here, so that's the map I'm going to use. And in fact, the spectrum, if M is equal to 1, M is low, it's not resembling at all the PDF. But if M is large enough, 10, so 10 is my approximation of infinity for this experiment, is exactly what you wanted. So I can take this map here, which has a uniform probability density function, to obtain this measurement result. So that's the original clock. That's the U-shaped in case you use a sinusoidal frequency modulation. That's a QB profile flat, so better. And the chaotic one is 9-10 dB less than the best possible methodology that was used in the commercial product. We also implemented a prototype of a split-spectrum clock generator for serial ATA. Serial ATA is a standard for transmitting serially data on your PC, and actually give the possibility of using split-spectrum technique to reduce EMI. So we implemented this in UMC 0.18 CMOS technology a few years ago, working at 3 GHz, and these are actually the measurement results. So you get basically 14 dB peak reduction with respect to the unmodulated cases, and 5 dB better than any other technique that was present in the literature at that point, with 1/3 of power. And with that, I think I'm going to stop here. And just I have some conclusion to go. Okay, let's skip these details here.
Sorry, I have a question about
Yes?
the spectrum that you
Sure.
chose.
This one, the previous one, that one you did. Okay, so I need to find the right slide, which is, as you can see, there are many more in the presentation, but I'm not given to show you. So and all the questions are probably okay. This one you want to see, right? Oops. Okay. Hello.
Yeah,
Okay.
that.
Yes.
So are these measurements done with different resolution values?
Ha ha.
Because
Ha ha. You really want a couple of punishment slides. It's no, I mean, very good question. So in fact, there is a huge issue here related to how you are measuring your spectrum. So all the results here are with respect to the theoretical spectrum, between quotes, and therefore you need to use a resolution bandwidth which is as low as possible in order to go as close as possible to, if you want to measure the spectrum. As you can see, the resolution bandwidth here was 100 kHz, and this was the same. We used exactly the same resolution bandwidth that that all the people that were producing prototype for serial ATA were using in order to make things comparable, because you are right, the spectrum depends on the resolution bandwidth. But there is a huge issue. The issue is that the norm for electromagnetic interference measurement specify which kind of resolution bandwidth you need to use and which kind of instrument that you need to use, which is a spectrum analyzer and not a digital signal analyzer. And this open up a huge thing, because what is optimizing the spectrum is not optimizing the measurement done with respect to that. And these are exactly the two slides that I left out. So if you take into account the spectrum analyzer input-output relationship, and you can do that in an analytic form for the triangular modulation and a semi-analytic form for the chaotic modulation, what you end up with this plot. That's the reduction of the peak as a function of the modulating index. And if you just take the spectrum, everything goes down till the point in which you are enlarging everything so few that you are inside the resolution bandwidth, and therefore enlarging the resolution bandwidth so that you are including the frequency deviation, so you don't spread anything at that point, and therefore you cannot reduce it anymore. So, but it's if you just take into account the input-output relationship, this curve has a minimum, and so there is this minimum means that there is an optimum point. And the interesting point is that if you go to see where all the commercial products are, none of them is in the minimum, because basically nobody has taken so far this into account. So there is still optimization to go for this product. And this was actually, we came up to this fact because people from Texas Instruments we are working with were telling us, no, split spectrum doesn't work, because our clients are complaining that, I mean, what we give to them is not working. And in fact, they were using the wrong modulation parameter. They were very far from the minimum here, and where actually the methodology doesn't work due to the input-output relationship of the signal. But anyway, again, very good point. So let me arrive to conclusion. So in terms of the second part, so we've seen that, you know, again, playing with statistics helps, and can actually, in terms of reducing electromagnetic interference, actually there is also a way in which you can design one of these chaotic maps, which actually turns out to be derived by a really minimal modification of a pipeline A to D converter. So you can turn it into a reconfigurable true random number generator. which was kind of interesting, and I can give you details if you're interested in too. But again, playing with this can actually help in several possible applications. To move on, basically, I think that especially the compressed sensing part could be interesting for, in general, the Internet of Things. One thing that you mentioned is that if you use compressed sensing, actually you can prove that you can actually use the decoding stage to embed some privacy in the telecommunication. So if you assume that you don't know entirely or you don't know at all the decoding matrix, so the matrix that you have used to acquisition, you cannot reconstruct the signal, so it gives you some privacy, and we studied this in terms of attack, so there are results on that. We are working also on switching power converters. Again, if you just try to do a little bit of theory behind this, you can actually come up with better way for implementing those. And also, one other important point is that there is no need, if you acquire signal using compressed sensing, to reconstruct the signal if you just can do your processing in the compressed domain, and that's, I think, the right way to go. And also, one thing that we need to look at is that if rakeness is also used in the decoding stage, so in all the decoding algorithms, are they going to be better if you acquire the signal using the rakeness and take this into account or not? We have preliminary result that says that this is the case, so there is work and activity also going on there. And let me conclude with a sentence which is attributed to Maxwell that I like very much, that there is nothing more practical than a good theory, or at least it helps to think a little bit out of the box. Thank you so much.
Okay, so I think we had quite a few questions, and given the time, if you have more questions, we can join the discussion and we can continue there. So
I have a little gift for our speaker.
Thanks a lot.
Take it out. So as you can see, it's in a beautiful
Bag.
ECE bag, so that you can carry it home.
Cool.
Then, let's see here. If I can find a way to open it, that is. Ah, there we go. And you can then take it out. It's a cool clock.
Pretty cool.
Yeah.
Yep. Wow.
Yeah, so you go
and it goes and actually
goes all the way around. And
so it's a gyroscopic clock.
Yep.
Pretty cool. Thank you so much.
Wonderful.
Thank you, Ralph. Thank you, Ralph.
Wonderful talk.
Thank you.